Welcome back. We're in section 3.3. And first of all, think about how far you've come. I mean, we started back in section 1.1. You've learned a lot of material already about linear algebra and some cool applications. So hopefully you're proud of the work that you've accomplished to this point. But here we are in section 3.3. We are going to continue talking about determinants, specifically about matrix inverses and systems of linear equations. And one of the applications that we talk about today, or one of the tools, I should say, that we talk about today is Cramer's rule. And Cramer's rule is a tool that seems to come up a lot. You'll see it probably again, and I know it's a totally different spelling, but we cannot talk about Cramer's rule, different Kramer, without sort of paying homage to this Kramer. So here's the story with determinants. It's really easy to get lost in the minutia of everything that goes on with determinants. So I want us to think for a minute about where we've come and what we're going to see in the future regarding determinants. Let's just pull back a little bit and think about why the heck are we doing all of this? So think about our determinant journey so far. It started back in section 3.1. That was the very first time that we even mentioned the word determinant. Up until then, we were pretending we didn't know what it was, or we didn't know what it was. Some of you have seen it before, but we didn't even mention it before section 3.1. So if we think of this determinant journey as sort of this long winding path, the very first thing we did was we talked really briefly about why we would even care about determinants, and that came at the very beginning of chapter 3. We didn't spend a lot of time on this because we knew we were going to talk about this more later, but we did briefly talk about why we would care about determinants, and then we spent a heck of a long time learning how to find determinants. So finding determinants was really all of section 3.1. And this was with cofactor expansion, and in the 2x2 case there was kind of just a super easy way to do it, and we even found an easy way to do it with the 3x3 case and some diagonals. So it almost seems a little backwards, but before we really dove deeply into why determinants are useful, the very first meaty thing that we did was we talked about the whole big process of finding a determinant, and that cofactor expansion and the term minor came up, and knowing how to do this was important. So then as we're walking along on this path, the very next thing that we spent some time on was the idea of properties of the determinant. So sort of these algebraic properties, and really helpful was the idea that you could split up the product of matrices. You know, if you're finding the determinant of a product, you could split that up into the product of the determinants, and that's super helpful. And some other things with like the transpose, how that affects the determinant. We talked about elementary row operations, how those affect the determinant. So once we knew how to find the determinant, we talked about some of the implications, just algebraic implications and properties of the determinant. And this may be why I think it's really hard to kind of it's really easy to get lost in this journey of the determinant, where we're talking about a lot of theory. Well, this is a process, and then a lot of theory before we really get to why do we care about these things. And we are going to talk more about why we care about these things today, but it's hard to talk about why we care about them without first knowing these things. So today's a little bit of a payoff day where we kind of wrap things up in a good way. And past section 3.3, we would get into some really cool things with the determinant. So we finally get to see in a deeper way some of the uses of the determinant. And we'll see that it becomes really relevant in terms of invertibility of a matrix. You know, we know that not all matrices can be inverted, and solving systems of equations in a different way than we've seen before. So all of these are helped by the determinant. And then later in the journey, we're going to see something called eigenvalues and eigenvectors, and those are super duper powerful and really cool. So the determinant does lead to some cool results and cool applications, really powerful tools, and we're just on the cusp of learning all of those. So in this section, we'll be talking about this. This is us, kind of looks like a zombie a little bit, but and then we're going to get past, the idea of how determinants help us with invertibility and solving system of equations, and we'll talk about eigenvalues and all of the cool applications that fall out of that. So you've been super patient because we really were heavy on the theory to begin with, but now we get to see some of the kind of payday of learning all this theory about determinants. So here's how today's going to go. We're first going to talk about an important formula. Then we're going to see a theorem. Then we're going to see another theorem. Then we're going to see a second formula. And then we'll conclude everything. Okay, what's the difference between a formula and a theorem? A theorem is a statement of a truth relationship. And a formula is you're going to find something. So these theorems are statements of truth relationships, and this is what drives mathematics. This is what how we discover certain things are true. This is the more abstract side of mathematics. And then these formulas, we use the theorems to create these formulas, these equations, where we're able to actually find things that we want to find. So in mathematics, there's two kind of general branches, pure and applied mathematics. And my husband's actually was a math major too in college, and he loved the applied math, and I studied more of the pure mathematics. And he always tells people that I studied the math without numbers, which is more like all these theorems, and he studied the math with numbers, which is taking those theorems and applying them and using them. And he's right. I love the pure mathematics where I don't have to worry about applying anything, but most of you probably are engineers who are anxious to use what we're finding in a practical way, and that's awesome too. Okay, this second formula that we're going to see later is Cramer's rule. So this is the actual Kramer, who Cramer's rule is named after. He probably deserves a little bit of attention also. So formula number one, which actually is a theorem too, so sometimes these overlap a little bit, is going to be a formula for finding A inverse. You probably remember back in section 2.4, we spent a lot of time learning about how to find the inverse using reduced row echelon form. And that's a totally valid method. It is limiting in certain ways. It only works for a particular matrix. You have to know which matrix you're dealing with. And we want to generalize things in a way that we can find A inverse in a more theoretical, in a more abstract way, where say that we didn't know the numbers that went in the matrix, say we had like A, B, C, D, E, F, or whatever, and we wanted just kind of a more theoretical way of finding the inverse for a general matrix. So we start with a square matrix A. So this is a formula for A inverse. We have a square matrix A, and you all remember what a cofactor is, like the cofactor of the element in the first row, first column. You're gonna the cofactor of this element here, you block out these rows, find the determinant of this, and then you have to think, is it plus minus plus minus? There's that involved in it as well. Okay, so think about those cofactors, hold those in your head for a minute. Then we're going to put each of those cofactors into a matrix. So remember, each of these cofactors actually takes quite a bit of work to find. You're blocking out rows and columns and finding the determinant of what's left behind. So each of these numbers is not trivial. It takes some work to find each of these. But just hold on for a minute. So this is going to be the matrix of cofactors. Then we're going to take this matrix and we're going to take the transpose of it. So each of these rows is now going to become a column. Let me write it like this. Each of these rows is going to become a column here. This row will become a column here. So let's look at the transpose of this matrix of cofactors. So let's see, that would be the C11. So the cofactor of the 1, 1 position, and then we're taking that row and making it into a column. And this would be C21, C and 1. And all of these are filled in. So this is the transpose of the matrix of cofactors, and this has a special name. It's called the adjoint of A. So this transpose of the matrix of cofactors is called the adjoint of A. And this is the part we care about. Before we go any further in this formula for A inverse, which we haven't even mentioned yet, or we haven't even said what it is yet, let's get some practice finding the adjoint of a particular matrix. So say we're given this 3 by 3 matrix A, and we're asked to find the adjoint of A. And this is often abbreviated ADJA. Okay, think in your head, when I find the adjoint of A, is that going to be a number or is it going to be a matrix? So the adjoint is definitely a matrix. It's the transpose of the matrix of cofactors. So we need to go through this matrix and find each cofactor. There's going to be 9 cofactors. And this would be a good time to pause the video and see if you can find each of those 9 cofactors, and then we'll compare them with what I find. So maybe we can go through the first one together. The first cofactor, the C11, that cofactor, we're going to block out this column in this row, and so we just need the determinant of that, what's left behind, and that'll be -4 minus 18 is -22. Okay, so pause the video and find the cofactor of 1, 2, 1, 3, 2, 1, 2, 2, and so on for the whole matrix. Okay, I found all the cofactors, and just remember with the cofactors, you really do have to be careful of that plus, minus, plus pattern. You know, for example, C12, here's C12, so I block out these and I get -2, -0. So that would be a -2, but I know I'm going to have an odd number on the power of -1, so the -2 becomes a +2. So sometimes people forget, you know, there's that -1 to the I plus j. That's a part of the cofactor, and it'll make some of these elements, you know, the opposite of what you find the determinant of the remaining numbers. Okay, so hopefully these are the numbers that you got for your cofactors. That took a little bit of time, but now that we have those, everything kind of falls into place. So we're going to find the adjoint of A. We're going to put these cofactors in a matrix, but we're going to take the transpose of the matrix of cofactors. So the numbers that should go in here are -22, 2, 6, 9, -1, -3, and -12, 0, 4. Once you know what the adjoint of a matrix is, it's relatively easy to find the inverse of the matrix, and I'm going to give you the formula for A inverse right now. So A inverse is equal to 1 over the determinant of A times the adjoint of A. And we're going to assume that A is n by n and that the determinant of A is not equal to 0. If it is, that's a problem. Well, we'll see if it is, it's not invertible actually. Okay, if that's true, then this is the formula for A inverse, or the formula for A inverse, and it only relies on finding the adjoint and the determinant of A. So let's go back to this guy and kind of finish things up and find the inverse. We have the adjoint of A. Let's go ahead and find A inverse from here. The formula for the inverse of A also relies not just on the adjoint, but on the determinant of A. So I'm going to go ahead and find the determinant of A. I already know all these cofactors, so finding the determinant isn't too bad. What we'll do is we'll do cofactor expansion along the first column. I like that 0 at the bottom. And so what we get is A11 times the cofactor of 1, 1, which is -22, plus A21, which is 2, times the cofactor of A21, which is 9. And so that looks like -22 plus 18 is -4. This is the determinant of A. And so A inverse, we'll just be putting these two things together using this formula. Obviously, we want to be careful and not interpret this as any sort of absolute value. This is the determinant of A, which is -4. And so we start off with 1 over -4 times that adjoint matrix. And you could leave it like this. We have found the inverse, or you could multiply that 1 over -4, that -1/4 through each element and find just the one matrix without any coefficient out front. So here it is. Here is A inverse from this original matrix A, using the determinant, the adjoint, and this formula for A inverse. So at this point, we're like, okay, cool, this is a formula for A inverse. But really, I just kind of pulled this out of a hat. I mean, I didn't tell you why it was any of this. And so the reason why this is true, well, there's a proof involved, and that has to do with this theorem. And I'm going to give you a sort of sketch of the proof. We won't go into the details, but I want to kind of show you that this actually does come from somewhere. So I think you deserve to know at least a little bit about why this is true. And it all comes from thinking about this guy here. This is the matrix A multiplied by another matrix, the adjoint of A. So here's the original matrix A, and the adjoint was this matrix of, or the transpose of the matrix of cofactors. Think about multiplying this. When you multiply this row and join it with this column, we'll get the first element of that product matrix. So right in this first spot goes the combination of this row and this column, which is A11 times C1 plus A12 times C2, all the way down A1n times Cn. But whoa, this is actually, we learned that this is actually the determinant of the matrix A. Remember how you could expand along any row and find the determinant? This just found the determinant just by doing this multiplication. So what's going in this very first element is the determinant of A. It's a number, and what you're going to find as you go through this multiplication is along this diagonal, you keep getting the determinant of A all the way down. And if you do the multiplication, you keep going, you'll see that every other element is actually 0. The fact that this right here, this combination of a row and column will result in a 0, this is a little bit trickier to see, and honestly it's the hardest part of the theorem to prove, but essentially it is representing what would happen, the determinant of if you had these first two rows identical, that they were both row 1, and the determinant of any matrix where you have identical rows is 0. It happens again and again throughout the matrix except for these diagonal elements, and they will all be the determinant of A. So what we're essentially seeing is that the matrix A multiplied by the adjoint of A is going to equal, well, think about this. This is actually the identity matrix multiplied by the determinant of A. So this is equal to the determinant of A times the identity matrix of size n. And the determinant of A is just a real number, so we can divide both sides by the determinant of A. Maybe we'll write it like this. And what happens is it goes away on the right side, so we just have the identity matrix. On the left side, we get, because it's a gosh, what are those called? Scalars. We can rewrite this as A times, I'm just going to move that scalar in, 1 over the determinant of A adjoint A. All of that is going to equal the identity matrix. And when you have two matrices like A and this big long thing that are multiplying to become the identity matrix, they're inverses of each other. So this guy right here is the inverse of the matrix A. So that is where the formula comes from, and it's pretty cool. I mean, these are all logical steps, but it takes some creativity to make that relationship happen and to recognize that, whoa, when you multiply A times this type of matrix, you're getting something that looks like this. And it's a really cool proof. Okay, let's think through where we've been so far. We knew that we were going to talk about our first formula, and it's a big one. It's this guy right here, the formula for the inverse of a matrix. We had to figure out what the adjoint was, so we defined what that was, and we calculated an inverse, and then we talked a little bit about why this theorem, this formula even works, why it's true. But this is the guy that we'll use here. Okay, so I told you this was the plan for today, and we've just done that big old formula. Now let's talk about another theorem. And this theorem says A inverse exists if and only if the determinant of A is not equal to 0. We've talked about how some matrices don't have a multiplicative inverse, and this statement here, if and only if, just means that this logical statement goes both ways. That we can say you know, A inverse exists, then it's true that the determinant is not equal to 0. We can also say that if we know the determinant is not equal to 0, that the inverse doesn't exist. So that's this is a statement you'll see again and again in math that just means this implies this, and also this implies this. That's not always true. It's not always bidirectional like this. Sometimes we can only assume one direction. But in this case, if and only if it's a really strong statement, a really strong connection between these two ideas, they're essentially equivalent. Another way of saying that is if you know the determinant is not equal to 0, it's some number like 7 or negative 3/4, you know then that A inverse exists, that you could find it. Also, this tells us that if A inverse exists, we know the determinant is not 0. So in this theorem, we see the relationship between the invertibility of a matrix and the determinant of a matrix. These are really two, you know, we developed these ideas kind of separately. We never knew that they would kind of go together, but they definitely go together. Determinant not equal to 0, you know you have an invertible matrix. So let's look at a couple examples. Are the following matrices invertible? And we're going to use the determinant to find out. Our first matrix is this 2 by 2 matrix, A equals 3, 2, 7, 1. And all we have to do is figure out what the determinant of this is. And that looks like 3 minus 14, which is negative 9. And yeah, that's not 0, so it's definitely invertible. So at this point you may be thinking, who cares if a matrix is invertible? It's actually a pretty big deal, and it lets you solve a lot of problems if you know a matrix is invertible. So this is a question that comes up again and again in linear algebra and has all sorts of applications. So it is something that we want to care about. So we'll ask the same question about this matrix. Is this invertible? And we'll use the determinant to decide whether this matrix has an inverse or not. Probably do cofactor expansion along the bottom row here. So determinant of B is going to be negative 1 times, let's see, negative 28 plus 36. And then we have this 0 here. It doesn't matter. So let's see, this plus minus plus minus plus. And the other part of that expansion is plus 1 times 2 times 12 is 24. Minus 16. So this is a negative 8 here, plus 24 minus 16 is 8, so that equals 0, which tells us the determinant is 0, so this matrix is not invertible. So the determinant being 0 is like death to the invertibility possibility. So we'll say no, B is not invertible. And it's all because of this guy right here. This one was invertible because the determinant was a non-zero number. Okay, so we have talked about our formula for an inverse of a matrix, our theorem that you only can find the inverse of a matrix if its determinant is non-zero. Now let's move on to our next theorem, and then we'll build up to the big climax, Kramer's rule. Okay, for this theorem, we're going to start off by saying let AX equal B be a system of linear equations. And maybe you say, hey, that doesn't even look like a system of a linear equation. It looks like just one equation. But we recognize that A is representing a matrix, X is a vector of like x1, x2, x3, so on, and B is a vector of constants. So this does represent a system of linear equations. And why don't we step back for a minute, back to section 2.2, where we did take a system of equations that look like this, and we would put it into an equation where we were dealing with a matrix and then this vector of variables and then this constant matrix. So we can always put a system of linear equations into a matrix equation, and that's just what we're doing here. We're saying AX equals B, and so we have something like this. If you don't remember this relationship, it's a good idea to pause the video and kind of take a look at this and how it all fits together. Okay, back to our theorem, and I should say that we have n variables and n equations, so A is an n by n matrix. And then the relationship is that if the determinant of A is not equal to 0, then there's exactly one solution, and if the determinant of A is equal to 0, there's either no solution or many solutions. Okay, so if the determinant is not equal to 0, then things work out fairly nicely. Your system of equations will have exactly one solution. What we're finding is, when the determinant is not equal to 0, things work out, nicely, predictably. You can invert the matrix, you can find that one nice solution. And then when the determinant of a matrix is 0, a few things break down. You can't invert it. There's maybe no solutions to a particular system of equations, or maybe many solutions. It's just a different case. This is like the, nice predictable case here when the determinant is some non-zero number. And then this is where, oh, okay, something is a little off. There's either going to be no solution, or we have to go find all the infinitely many solutions. So whereas before we had a relationship between the invertibility of a matrix and the determinant of a matrix, now we see a relationship between the type. That looks really weird. Now we see a relationship between the type of solutions to a system of equation and the determinant of the matrix, of the coefficient matrix. Type of solutions of a system of equations and the determinant of that coefficient matrix. So once again, the determinant tells us some information about something that maybe wasn't obviously related to the determinant. So now, knowing what we know about how the determinant can help us to classify solutions, we can ask, will this system have a unique solution? And so here's the system. Whether or not this system has a unique solution only depends on the coefficient matrix and the determinant of that matrix. If it's non-zero, then it will, and if it's 0, then it won't. I think this is pretty cool, actually, that to determine if a system has a unique solution, we only need to look at the coefficient matrix. It actually doesn't even matter what these numbers are. Once we know the coefficient matrix, that A has a determinant that's non-zero, it really doesn't matter what these numbers are, we will still get a unique solution. So here's the system written in matrix form, and all I have to look is the determinant of this non-zero, and I'm going to use my calculator to find the determinant of this. I've entered that coefficient matrix, and so I'll get out of here, and then I just have to, that's not it, how about second matrix, go ask the matrix, here's the determinant operation right up here, and then we'll go back and pick up that matrix A and find the determinant of it. And okay, so you can't see that because this guy is, how about that? The determinant of that matrix ended up being 0. Okay, so the determinant of that coefficient matrix is 0, so there is no unique solution. And when I say unique, it just means that there's not one solution. There is no unique solution. It may be that there's no solution, period, or that there are many, but this was one of the cases that we knew is possible with a system of equations, and this is not going to happen. Okay, we've done all of this stuff. Now we're ready for Kramer's rule. This one was the formula for the inverse of a matrix. This one was that if your determinant is non-zero, you'll have an inverse. And this was if your determinant is non-zero to a matrix that's the coefficient matrix of a system of equations, then you will have a unique solution. So we've done a lot of this journey. We've talked about today the uses of the determinant as far as invertibility and solving systems of equations. Let's do this last little guy right here, Kramer's rule. And what this is going to do is tell us how to find the solution of a system of equations. And so Kramer's rule will give us a formula for x in the matrix equation ax equals b. So here's the setup. Let ax equal b be a system of linear equations. It has to be an n by n system where the determinant is non-zero. Then the solution is x1 will equal the determinant of a1 over the determinant of a. x2 will equal the determinant of a2 over the determinant of a, and so on until we get to xn, which is the determinant of an over the determinant of A. And each of these little guys, each of these determinants is a real number, so our x1 through xn are just real numbers fitting into this solution vector right here. Now I haven't told you really what A1, A2, and AN are yet. Where AI is the matrix obtained by replacing column I of A with B. So each of these guys, like this one right here, would be the matrix that you got if you replaced the first column of A with this, you know, the constant column, the B column, and this would be replacing the second column of A with B and the nth column of A with B, and then finding the determinants of each of those new matrices. Okay, this is an explicit formula that will give you the solution to any system of linear equations where the determinant is not equal to 0. So as an example, we're going to solve this system using Kramer's rule, and here we've got the system. Let's throw it into a bunch of matrices. A will be this matrix here, just the matrix of coefficients, and X will equal just our x1, x2, x3 vector, and then B is the 3 by 1 matrix, -2, -5, and 6. What we want to be able to do is say exactly what x1, x2, and x3 are, and Kramer's rule gives us a formula for finding each of those. I know I'm going to need to find a bunch of determinants, and I start by finding the determinant of A, and I'll go ahead and use my calculator to find the determinant of this. And the determinant of A ends up being -3. Okay, my next job is to find the determinant of A1, and that is, I'm going to replace, well, column 2 and 3 are the same, but then column 1 needs to be the B vector, so -2, -5, 6. This is A1, and I'm going to find the determinant of this. And interestingly, the determinant of that is -3. That won't always happen. It just is something of a coincidence that the determinant of A1 is the same as the determinant of A, just plain old A. Okay, let's find the determinant of A2. The first and the third columns are the same, but then I've got to replace the middle column, the second column, with the vector B. So I want to find, this is A2, I want to find the determinant of A2. The determinant of A2 is 6, and last but not least, we're going to find the determinant of A3, and this will be 1, 2, 1, 3, 5, 2, and then I need to replace that third column with -2, -5, 6. This is A3, and the determinant of this is -9. I've got my 4 determinants that I'm going to need to use, or have to use Kramer's rule, and so from here it's just kind of pulling everything out. So x1 should equal the determinant of A1, which is -3, over the determinant of A, which is -3. That equals 1. x2 will be 6 over -3, which is -2, and x3 is -9 over -3, which is 3. So the solution to the whole system is the unique solution 1, -2, 3. So I'm slightly paranoid that somewhere in all this work, maybe I mixed up a number or wrote something wrong. So I'm just going to go back and check my solution in the original system of equations. So 1, -2, 3. 1 minus 6 is -5, plus 3 is -2. That works. 2 times 1 is 2, minus 10, that's -8, plus 3 is -5, that works. 1 minus 4 is -3, -3 plus 9 is 6. Awesome, this really is the solution. Okay, let's talk about what we know at this point. If we want to find A inverse, we could either ask the calculator to do it. Sometimes we do that. We could use Gaussian elimination. That was the first way we learned how to find A inverse by hand, and that was the method where we would take the matrix A and adjoin to it the identity matrix, and we put it through reduced row echelon form until it came out looking like the first part was the identity matrix, and then what was left on the right, it happened to be the inverse of A. So we learned how to do that probably a couple weeks ago. And now we have another formula to find A inverse. So A inverse is just 1 over the determinant of A. This is the first time we've used the determinant to find the inverse. And then we also use this thing called the adjoint of A. So these are 3 ways to find the inverse of A. We also know if we have a system of equations, system of linear equations, and we want to find the solution, so finding x, we can use our calculator, which uses Gaussian elimination, or we can use Kramer's rule. So Gaussian elimination would help us solve it, but now we have another tool, which is Kramer's rule, which depends on the determinant of the matrix. So a lot of focus on this guy today, and a lot of focus on the ability to do this, both of them using the determinant of a matrix. This was sort of a little false conclusion. There's actually one more thing I want to talk about, which is a preview to the next section, and we're going to have a homogeneous system of linear equations and look at them, and it's going to give us a preview to the idea of an eigenvector. This will be a good example to end on. It forces us to remind ourselves, what the heck does a homogeneous system of linear equations, what does that mean, this word homogeneous? And you'll remember that it's a system of linear equations where all the constant terms are 0. So this is awesome. We're starting to really begin to tie in some loose ends, some ideas from different parts of the course so far. And this example will be a good preview to the idea of an eigenvector. So the first thing we're given is this equation, and this right here is the Greek letter lambda, and right now it's a variable. So lambda plus 2 times this x1 plus lambda plus 4 times x2 equals 0. Okay? So when we find the solution to this system, we're really looking for this x1 and this x2. Now there is something called the trivial solution. If this was 0 and if this was 0, it of course would be true. It would cause everything to be 0. If this was 0, if this was 0, again, of course it would cause everything to be 0. And that's called the trivial solution to a homogeneous system when you have your variables all equal to 0. It's not a very interesting solution, but it's one that always works for homogeneous systems. So we'll just make note of the fact that x1 equals 0, x2 equals 0. That is in fact a solution to this system over here. It's called the trivial solution. This type of solution will always work for homogeneous systems. A question that comes up though is there possibly another x1 and x2 that would work in this system? Okay, so we know the trivial solution always works for homogeneous systems, but the question we're now going to ask is there possibly another solution to this system? And I want you to think about what that would imply. If, in fact, there was another solution to this system, it would mean that there was not a unique solution. So this would imply, so another solution, let's draw this arrow down here, another solution would imply that the system does not have a unique solution. The system doesn't have a unique solution. And this goes both ways. And if the system doesn't have a unique solution, well, that implies both ways that the determinant of the coefficient matrix So you tell me, should this equal 0 or not equal 0? So a system doesn't have a unique solution. Should this equal 0 or not equal 0? and it should definitely equal 0, because that's what it means. If the determinant of the coefficient matrix equals 0, then we know that the system has more than one solution. And that's kind of what we're looking for here. We want to know, does this have a solution other than the one we already know about? If it does, then the determinant of the coefficient matrix has to equal 0. Well, let's throw these coefficients into a coefficient matrix and see what happens when the determinant is 0. So we want, let's see, lambda plus 2 is the first coefficient, lambda plus 4 is that one, 2, and then lambda plus 1. These are just coefficients. We want this to equal 0. And this equals 0 if lambda plus 2 times lambda plus 1 minus 2 times lambda plus 4 equals 0. So this is just the equation for the determinant, and then I did a little bit of algebra, just cleaning everything up, and I actually did find that this equation has a solution. If lambda equals -3 or 2, then we'll get 0 for a determinant, and just going back up through the chain of logical statements, if that determinant is 0, then the system will have more than one solution, and so that happens when lambda equals -3 or 2. Okay, so the answer to our question, is there possibly another solution than the trivial solution? Yes. And it happens if lambda equals -3 or if lambda equals 2. So if this was sort of the first part of the problem answering this question, then the next part of the problem is, okay, if it works, if there are more solutions, find the solutions for each of these values of lambda. Okay, so if lambda was equal to -3, we can just go back to this original system of equations and plug that in for lambda and see what the system is with that as our lambda. And so that would be -3 plus 2 is -1, so that's negative x1, and -3 plus 4 is 1, plus x2 equals 0. And then the next equation would be 2x1, and -3 plus 1 is -2x2 equals 0. This system has many solutions, and they're all of the form x1 equals r, then x2 would equal x2 equals r also. So they're all of the form r, where r is any real number. If lambda equaled 2, what would the system of equations look like? First of all, well, let's see. That would be 4x1 plus 6x2 equals 0, and then 2x1 plus 3x2 equals 0. This system also has many solutions, and they're all of the form x1 equals, well, let's start with x2. If x2 equaled r, then x1 would have to be -3/2 r. So maybe you're asking, where am I coming up with these solutions? And I'm not doing it exactly in my head, but I do know that I could solve this system using old methods that we have and come up with these as the solutions. Okay, this example was really just to get us used to a lot of things, working with these kind of new objects where we've got some lambdas. We're going to see why I even wanted to bring this up. And if there's a solution to this homogeneous system other than just 0, 0, then it really implies that the determinant of the coefficient matrix must be 0. And so we can find the exact lambdas where that happens. Once we have the exact lambdas where that happens, we can find the solutions to the system of equations. There are a couple examples like this in the homework where you have to construct some non-trivial, meaning non-zero solutions to a system of equations like this. And this type of problem is going to lead us to this big idea of eigenvectors, but it's all dependent on this fact that we learned today, that if the determinant of the coefficient matrix equals 0, then there is a possibility of more solutions.